Section 5.3, we are working on connecting f prime, f double prime, and the graph of f. We've already done a good bit of work with this earlier in the semester, so we are going to build on that, and we will start with reviewing the first derivative test, which we did in Section 5.2. The first derivative test is used to find maxes and mins and to find intervals of increasing and decreasing. So the summary of the first derivative test is here. The function that we'll be working with is here. So to do the first derivative test, we'll need to find the critical points, which are the x values where f prime of x equals 0 or is undefined. And we have that down here in number 1. Y prime is equal to 6x squared minus 28x plus 22. And we want to factor that. This is a quadratic polynomial, and that's defined everywhere, so the derivative is not undefined anywhere. So we'll factor and set it equal to 0 to find where the derivative equals 0. So we've done that here, and our critical points are 11/3, x equals 11/3, and x equals 1. Here are our critical points. Now we build up intervals around our critical points. And when I say that, this is an open interval. We don't have any endpoints, so we're going to go from negative infinity, coming from the far left to the first critical point, which is 1. Then we will have from 1 to 11/3, and then we will have from 11/3 to infinity. We'll pick a test value in each one of those intervals, and you'd want to just pick a number that's in the interval that's easy to work with. So I chose 0, 2, and 4. We plug those test values into the first derivative, and all we need is a sign. We don't care about the number, just the sign. So if I plug 0 into this nice factored form right here, it makes it very easy to figure out if we're positive or negative in that interval. So plugging 0 in, we get a negative times a negative, giving us a positive, which means the original function f is increasing on the interval negative infinity to 1. We do the same with 2 and 4, and in the second interval we get a negative, and in the third interval we get a positive. So we have a situation where our original function is increasing, then decreasing, showing that we have a max, and then we are increasing again in this interval, showing that we have a min. So this first derivative test gives us a lot of information. We know that we have a maximum at the first critical point at x equals 1. We have a minimum at the second critical point, which is 11/3. We know that we're increasing in the intervals from negative infinity to 1 and 11/3 to infinity. And we're decreasing on the interval from 1 to 11/3. We also can see that we have no absolute max and no absolute min, because to the right of 11/3, this function continues to go up forever, and to the left of 1, it continues to go down forever. So we have a relative max and a relative min, and no absolute max or min. All right, the second derivative test is used to find maxes or mins. It is not used to find intervals of anything. We just use it to identify maxes or mins. And the way that we do this is we find a critical point, and we determine if the function at that critical point is concave up, which would mean we have a minimum, or at the critical point, is it concave down, which would mean we have a maximum. So to do this, we find our critical points, we find the second derivative, which tells us about concavity, and we plug the critical points into the second derivative. If the second derivative is positive at the critical point, we're concave up and we have a min. And if the second derivative is negative at the critical point, then we're concave down and we have a max. So doing this for the problem that we started on the previous slide, we found our critical points to be 11/3 and 1. And our second derivative is 12x minus 28. So we will plug 11/3 into 12x minus 28. We get a positive value, which means at that critical point we have a minimum. And we'll do the same thing for x equals 1. We evaluate the second derivative at x equals 1. 12 times 1 minus 28 gives us a negative, which means that we have a maximum at x equals 1. The one downfall of second derivative test is it can fail. And you could, when you're evaluating your second derivative, it could come out to equal 0, which means that you would have to go back and do the first derivative test to find out what's going on, to see what's happening to the left and right of these critical numbers. So that's the only downfall of second derivative test. You may try it, it may fail, and then you go back and do first derivative test. Otherwise, you can use first derivative test or second derivative test as you wish, whichever one you're more comfortable with, to find your maxes and mins. And then our last test that we want to talk about is the concavity test, which is very similar to the first derivative test, but it does not find intervals of increasing and decreasing. It finds intervals of concave up and concave down for the original function. So it works the same way as the first derivative test, where we will find the second derivative. We will find where the second derivative equals 0 or is undefined, and these points are called possible, we don't know for sure yet, points of inflection, and I'll refer to them as PPOIs. So once you find your PPOIs, then you can set up intervals around them, pick test values, and plug your test values into the second derivative to identify the concavity in the interval. So our second derivative was 12x minus 28. We set that equal to 0. 12x minus 28 is not undefined anywhere, so we'll just find our critical points by setting it equal to 0. We get a critical point at x equals 7/3. Now we will set up our intervals around 7/3, pick a test value in each of the intervals, and evaluate that test value in the second derivative. From negative infinity to 7/3, we get a negative value when we plug in 0. When we plug in 3, we get a positive value. So that means the original function is concave down on the interval from negative infinity to 7/3, and concave up from 7/3 to infinity. And what that also means is that we have a point of inflection, because a point of inflection is a point where the concavity changes. And we have just performed an analysis to show us that the concavity changed at 7/3. So we have a point of inflection at 7/3. If we were concave down to the left and concave down to the right, then this would not be a point of inflection. There needs to be a change in the concavity. Excuse me, I hope this helps. Let me know if you have any questions. Contact me in class. Thanks.